Hello everybody, we're going to carry on here on the next page of the class notes for section 7.2. We're getting towards the end. We just got to do some of these examples where we are not dealing with a standard normal distribution anymore, but it's not going to be a problem because the calculator is going to be a workhorse for us on this one. I mean, if we needed to, we can convert data values to z-scores, and we can do that, but we actually won't really need to because we're just going to be able to keep using normal CDF and just put the numbers in how we have them. So why don't we see this example? Women's heights, according to this, are normally distributed with an average of 63.6 inches and standard deviation of 2.5 inches. We want a probability that a randomly selected woman will be taller than 62 inches. So remember, the probability, that's just the area under the normal curve. So the mean there, which is in the middle, is the 63.6. So actually 62 is a little bit less than that. So maybe we'll say 62 is, somewhat less than the mean. We want the probability that this woman's going to be taller than this. So we want to find out the area that's to the right of this value. And so we can do that by going over to the normal CDF, which was number 2. The lower bound in this case is 62 because we want to find a woman who's taller than that. So the lowest her height can be a 62. The upper bound, this is where we want to use our quasi-infinity value. And then the mean in this case actually is going to be something different. We will change this one because the mean is 63.6. And the standard deviation also is 2.5 inches. So we will go 2.5 with this one. And now, what is this area? The area over there, which is the same thing as the probability, is going to be point. And remember, we rounded this one to 4 places. 7, 3. Looking at this one, 8, 9. That would be the probability there, 73.89%. So now we want to find out what's the probability that she's going to be between 64 and 71 inches tall. So 64 is just barely more than the mean. So maybe if the mean is here, we're looking for, she's going to be a little bit taller than the mean, or anything up to 71 inches, which 71, how many standard deviations is that above this mean? We could actually calculate that one. What is the z-score, by the way, for 71 inches? To find the z-score, we will do 71 minus the mean, because we're doing the data value minus the mean using this formula. 71 minus the mean of 63.6. And then we need to divide by the standard deviation. So that's a z-score almost of 3. So that's going to be way over on the tail. And then we want this area, because that'll be the probability that she is between these two heights. And we will just go to the normal CDF, and then the lower bound for us this time is going to be 64. The upper bound is 71. The mean standard deviation is the same. So that area is like we could have predicted. The area is almost half. So it's actually 0.43, 4, and then 9. Very good. Now we will see, what about for this one? Talking about reading speed. Apparently it's normally distributed with a mean of 125 words per minute, standard deviation of 24 words per minute. Now we want to find out what is the probability that this person has less than 100 words per minute. So you draw a very funky looking normal distribution. The mean is 125. We want less than 100, so that's going to be, oh, do you see the standard deviation is 24, so it's a little bit less than one standard deviation away. This z-score, it must almost be -1, a little bit, what is it, more than -1? It is more than -1, barely. Why don't we find that z-score just for fun of 100? It's 100 minus 125. And then we will divide by 24. So the z-score for 100 words per minute is -1.04. So that was a lot of fun. But we're interested in a probability, so we want to get this tail that's to the left. So why don't we do it? Sorry about that shading job. But the lower limit, since it's going like to -infinity, we use our substitute for -infinity, which is the negative Google. Then we use the upper bound is 100. We want them to read less than 100 words per minute. The mean is 125. Standard deviation is 24. What is that area? So glad to know that the area is 0.14. We have to round it to 4 decimal places, so it's going to go 88. That would be the probability, 14% chance. And now we're getting into some of these where we actually already know the probability, and we want to find the corresponding z-score. So it's kind of like the ones before. It's just that now it's not the standard normal distribution anymore. We have a different mean and standard deviation than the one where it's just z-scores. So how about this? Women's heights. We got a mean of 63.6, standard deviation 2.5 like before. This modeling agency, they only want the tallest 10% of women. So we want to find the z-score here, or in fact we want to find the height, where this little shaded area to the right of that height is 10%, which is 0.1. So we will go to the distribution, inverse normal. The area that we want is 10%. In this case, the mean is 63.6. The standard deviation is 2.5. And we want that tail to be on the right. We want these women who only are very tall. So that's the height that we're looking for. What is the cutoff height? They must be at least 66.8 inches. Is that even very tall? That's only 5 foot, well, it's almost 5'7". I guess it's fairly tall for a female. Inches. And then, let's see. I can't read the top of that one. What is the cutoff? Oh, so I did it there. This work is supposed to be this stuff, about 66.8 inches. That was the answer there that we just found. And now we're talking about the reading speed again. Here, this psychologist, they want to determine stuff about unusual students. So we want to determine the reading rates of the middle 95% of all 6th grade students to find out who is unusual. So the middle 95%, it's going to have 95% of the area in between the tails. So all of this area is supposed to be 95%. That's just in between these 2 points. So why don't we go to the inverse normal, number 3. The area needs to be 95%, which is 0.95. The mean words per minute was 125. 24 is the standard deviation, and we want that tail in the center. What kind of an output are we going to get? It's so nice. the reading rates for unusual. If somebody reads less than 77, why don't we just call it 78? If somebody reads less than 78 words per minute, or they read more than 172 words per minute, they will be considered unusual. So it's very interesting. And now we're talking about IQ scores for this next example. It's normally distributed with a mean of 100, standard deviation of 15. We've seen it before. People are considered intellectually very superior. It's a very nice terminology. If their score is above 130, what percentage of people fall into that category? So we're interested, what is the percent of people who have an IQ above 130? Well, we know the mean is 100. The standard deviation is 15. And we want to find out the area that's above 130. So it's going to be kind of 2 standard deviations over here. We want to find this area in this little right tail. Now to find the area in the tail, we don't want to use inverse normal. That's the one that's just normal CDF. That gives us the area. The lower bound is 130 because that's on the left. We want stuff that's above that. So we're going to use our little infinity substitute. In this case, the mean is 100, standard deviation is 15. So it appears that it wants the percentage, by the way. So this number as a percent, can you tell me what it is? Looks like 2 point, we can round it, 2.28%. It's not clear how much we should round this one, but I think it's a pretty good answer. And then we're getting ready to wrap this one up. These are the last examples that we're going to find. What about, we're still talking about these IQ scores. Now we're referring to somebody who is intellectually very superior. They're going to be the top 1%. So we want to find this area, this little bitty tail that has an area of 1%, which is like 0.01. That needs to be the area for this little tail. So how are we going to do it? If we already know the area and we want to find the IQ score, that is the inverse normal. So we go to our inverse normal. The area needs to be 0.01. The mean was 100, standard deviation is 15, and we want the tail to be on the right because we want the very superior people. So that'd be an IQ of 134. And IQ scores, seems like they're usually whole numbers. I'm going to just round it, call it 135. So that would be even more superior intellectually. And then last but not least, we have this example to wrap things up. It's about the length of human pregnancies. I wonder if you guys can tell me what kind of animals have very long pregnancies. Have you ever heard of how long an elephant is pregnant? It's amazing. It's a very long time. However, the lengths of human pregnancies, they're approximately normally distributed with a mean of 266 days, standard deviation of 16 days. So there's this letter, it's about a wife. She gave birth 308 days after a brief visit from her husband who was serving in the Navy, so it's kind of a tongue-in-cheek little adult fiction. Given this information, find the probability of a pregnancy lasting more than 307 days. That's a different number than this one, but we're going to go with the question. 307 days. The probability that it's going to be more than 307 days. So let's see. The mean is 266. Standard deviation is 16. we want to find the probability, in other words, we want to find the area that's above 307. So if we want to find an area, that means we want to go to the normal CDF. The lower bound is 307. The upper bound, it's just going off into infinity. And then the mean is 266. The standard deviation 16. We will find this area. Wow, it's so improbable. It's only 0.5%. It's 0.0, but of course we want these areas to be to 4 decimal places, 0052. That's the probability. So it's very unusual. Now what about, we're going to talk about somebody being premature. The length of the pregnancy is in the lowest 4%. So we're trying to find such a pregnancy period that the area to the left, that area ended up being a little bit bigger than I wanted, should have an area of 0.04. If we already know the area, I'm going to get rid of those numbers. If we already know the area, we need to use inverse normal. The area is 0.04. The mean is still going to be 266. Standard deviation of 16. And the tail is on the left. So that would be a pretty short pregnancy. It's really not too short though if you think about it. It's 237, but if we round that one, why don't we just call it 238 days? That seems pretty reasonable. So that's the end of these examples, and actually it's the end of 7.2. Thanks for watching.